In this video, we're going to talk about measures of variation. So I'd like you to consider the following two data sets of weights in pounds of dogs visiting the vet. So the first data set is the weights of 5 randomly selected dogs visiting the vet. And there are those 5 weights below in pounds. And the second data set is a set of 6 randomly selected beagle dogs visiting the vet. So there's 6 weights of beagle dogs visiting the vet, again in pounds. So I'd like you to look at these two data sets and think about how would you describe the main differences or the main difference between these two data sets. There might be more than one thing you could say here. And does this main difference, the thing that makes these two data sets especially different from each other, make sense in context? In other words, where the data is coming from, the first set being 5 randomly selected dogs, and the second set being 6 randomly selected beagle dogs, so a specific breed of dog. So I'd like you to just think about this for a moment and pause, and we'll talk about it together in just a moment. Okay, so what are the main differences, or what is the main difference between these two data sets? So some things you might have explored would be, say, measures of center, like we talked about in previous videos. So we talked about the mean, so the sample mean. And the sample mean in this case, if you calculated it, would be 27.4. Feel free to check just as a way to do an extra practice problem. And the sample mean for this set of data ended up being 25.8. So again, this is the sample mean. And the sample median, another measure of center, the data in the middle of our data set, or the middle data value in this case, is 26. This is the median. And the median for this other data set, for the beagle dogs, is 25.5. And again, you could try these out just as an extra set of practice problems. So one other measure of center we did was the mode, not as necessarily useful of a measure of center, but in this case there is no mode. There's no data value that occurs more than any other data value, whereas in the set of 6 beagle dogs, there is a mode. 24 appears twice, so the mode in this case is 24. Okay, so looking at these measures of center, I would say that this is not the main difference between these two data sets. This is not what makes these data sets clearly different from one another necessarily. So when I compare the two means of 27.4 and 25.8, when I compare those two, these are pretty similar. So the means are pretty similar to each other. What else could I compare? I could also compare the medians, 26 to 25.5. Again, they have similar medians. And this is a difference, but I don't think it's an incredibly important difference. So this is a little different. There is one repeated value, but I would say that this is not sort of an essential difference in these two data sets. There might be other data sets where a mode is really important. If some value is repeated over and over and over in one data set and not in another, that might be of interest in other cases, but I would say here it is not particularly interesting. So what is the main difference in this case? I would suggest that the main difference is how spread out this data is. So these data values, 26, 34, 6, 11, 60, these data values are more spread out. And these data values down here are less spread out. These data values are closer together. There's less difference between the data values 20, 24, 24, 29, 30, 27, 31 than there is between these data values. So these data values, again, more spread out farther apart, and these data values are less spread out. They are closer together. So we said that the main difference between these two data sets is the level of variation, or how much the data is spread out. So we saw that this data is more spread out, and this data is less spread out. It's more clustered together. And does this make sense in context? Well, yes. So here, this is some 5 randomly selected dogs visiting the vet. They could be, any breed. And so, maybe this is a Chihuahua, and this is a sheepdog. They can be all different breeds, and because they're randomly selected dogs of no specific breed, we would expect more variation in that random sample. Whereas here, all the dogs are of the same breed, so these data values are closer together. They're all beagles, and if they're adult dogs that are beagles, there's going to be some range of expected values for the weights of those dogs of specific breed that is smaller than the range of all breeds of dogs' weights. So yes, this does make sense to us in context. Notice that the sample size, n equals 5 and n equals 6, really has nothing to do with this difference. Okay, so we are going to talk about 3 ways to measure this idea of how spread out a set of data is. So we're going to talk about 3 measures of variation, and those measures of variation we're going to talk about are the standard deviation, the variance, and the range. For us, the standard deviation will be the most important one that we talk about the most often, but these 3 different measures, standard deviation, variance, and range, they will all be larger in the case that the data is more spread out, and they will all be smaller in the case that the data is less spread out. So let's first talk about standard deviation, which, as I said, is going to be our most important measure of variation, or how spread out a set of data is. The standard deviation of a data set measures how much data varies around the mean. So how much data is far apart from the mean, that measure of center. The standard deviation will be larger when the data is more spread out and smaller when the data is less spread out. In terms of notation, the standard deviation of a sample is given by lowercase s, and the standard deviation of a population is given by sigma. So for a sample, we have lowercase s, and for a population, we have sigma. As we saw before, it's generally the case that when we talk about a parameter, we use sort of fancier letters, like this Greek letter sigma. So this is sigma, and this is a lowercase s in Greek. So we saw before the uppercase sigma for some. We'll see that again shortly. And this is a lowercase s. So when we're talking about a statistic, when we're talking about the standard deviation of a sample of values, we use lowercase s. When we're talking about it for an entire population, we would use sigma. Okay, so now let's talk about the formula that gives the standard deviation of a sample. So the standard deviation of a sample S is given by the square root of the sum of each data value minus the sample mean squared divided by the sample size minus 1. So we'll break that formula down in a moment. Okay, so the standard deviation again is given by S is equal to the square root of the sum of each data value minus the sample mean squared divided by the sample size minus 1. and all of that is inside the square root. So let's talk about why this measures the amount that the data varies around the mean. So measures amount that data varies from the mean. Okay, so first of all, each individual value, x minus x bar, this is the distance from each value to the mean. So distance from each data value to the mean, x bar. So again, little x is a data value and x bar is the sample mean. So distance from each data value to the mean, yeah, that makes sense that would help us measure the amount that the data varies from the mean. Okay, so in the next step, we square those before we add them together. So x minus x bar squared, this is squaring that difference. Why would we do that? So we square difference between x and x bar, the difference between the data value and the mean. Why? So our next step is to add those differences together. What would happen if we just added without squaring? If we just added the sum of each of the differences, x minus x bar, without squaring, what would we get? We would actually get 0 every time, because some of those differences are going to be positive and some of those differences are going to be negative, and we would always get 0 because of how the sample mean is defined. And getting 0 every time obviously would not be a very good measurement. It basically wouldn't tell you anything if the standard deviation was always 0. So we square the differences between x and x bar, between each data value and the mean, so that the values won't cancel each other out. So these values are non-negative. We know that squared numbers are always greater than or equal to 0, and they won't cancel each other out. Okay, so our next step is to sum those squared distances together. So we do the sum of x minus x bar, each data value minus the sample mean squared. We sum or add together these squared differences. So we're adding those values together. Let's separate those two. We sum these squared differences, adding those differences together. Our next step is to divide by n minus 1. So we take the sum of the squared differences, squared divided by n minus 1. And this is sort of like averaging these squared differences. So this is like averaging those squared differences. If we were dividing by n, remember n is the sample size, this might make more sense intuitively if we were just dividing by the sample size. However, there is a reason that we divide by n minus 1 instead. It's because of the number of degrees of freedom that we have. If we have n data values, then you can find the nth data value based on the information that is provided either by the mean or the standard deviation. And so there are n minus 1 data values that are essentially independent from one another if you already have the mean or the standard deviation. So I won't ask you for that in particular, but in case you're curious, that's why we use n minus 1 instead of n. And the very last step is to do the square root of the whole thing. the square root of x minus x bar squared divided by n minus 1. So all of this is inside of the square root. And the reason that we square root at the end, so square root at the end, to sort of bring the size of the standard deviation back down to the magnitude of the original data values. So this is to bring the size or the magnitude of the standard deviation back to the size of the data values, because squaring those differences, if those are values greater than 1, is going to make them a lot larger. If those are values between -1 and 1, it'll make the values a lot smaller. So again, this is the formula for the standard deviation. Again, the sum of the differences of each data value minus the mean squared divided by n minus 1, where n is the sample size. And to me, the most important thing is to understand why this formula, why this measures variation, in particular variation about the mean, how far apart most data values are from the mean, kind of on average, and just generally understand what standard deviation tells you. That standard deviation tells us how much, how large the variation in the set of data is. So I want you to understand what standard deviation is. For the most part, I'm not really going to ask you to calculate this value over and over. So I'll ask you to calculate it by hand once. But for the most part, what I really want you to do is understand where it comes from and what it measures, and I'll ask you to calculate it by hand once. So in the next video, we'll do a couple calculations of the standard deviation using the formula we just described. The first example we'll do is finding the standard deviation for those randomly selected beagles. And so if you're feeling brave, you could give it a try with with the formula above, and then see in the next video if you did it correctly, or if you feel like you want to see an example first, feel free to go straight to the next video.